All right, for the SPSS examples, I'm going to show you the ones from the PowerPoint, from the chapter, rather than do the homework for you. This one was chapter 12, example 1, page 535. All right, so we were looking at the one where do children's IQs differ based on level of lead in the blood, rather. So let's go to variable view. I went and hand entered all of those data, and then I value labeled low, medium, and high. Okay, so it's very simple. I just go to analyze. Oh no, before I do that, let's go ahead and go to analyze, explore, and we're going to bring our dependent variable over, and we're going to bring our lead, uncheck stem and leaf, and check normality, say okay, continue, and say okay. Takes a second. Here's our case processing summary. Here's our test of normality, and we can see that at each level of our factor, we have normal distribution. So that's been taken care of. So we know we have normally distributed data in each level of our factor. So let's go to compare means. Whoops, come to one-way Anova. Bring our IQ over to the dependent variable, bring our lead level over to the factor list. We're just going to click on post hoc. Everything keeps popping up on the other side. We're just going to do, we could do Tukey, or any of these really would work. The ones that I'm the most familiar with are least significant difference, which is actually the most lenient. Bonferroni's pretty strict, which means you'll more find significant differences among the groups with a least significant difference or a Tukey than you would with a Bonferroni. The book talks about Bonferroni. These are just, and Chaffee is the most strict. These are just different post hoc tests to see if there's, to do multiple comparisons between the levels of the factor. So these ones here, low, medium, and high. We're checking low to medium, low to high, medium to high. And I always do LSD just because it's easiest. It's the first one to check and it's the easiest to interpret. But you could do Bonferroni, you could do Tukey, you could do Chaffee, Duncan, Dunitz, all these different ones. But we'll just stick with that one. Okay, so say continue. Options, we click on options. Oh, it popped up over here. We want descriptives, we want homogeneity. We're going to say continue, and we're going to say okay and check our output. All right, so let's look. The low blood lead level had a mean of 100 IQ. The medium blood lead level had 94, and the high blood level had a 94. So these guys don't look significantly different from each other, but they may both be significantly different from the low group. Let's check our homogeneity of variances, and it's not significant, so we're good. So we check both assumptions. We are normal and we are equal variances. Now let's come down here and look at our Anova table. We have our between group mean square and our within group mean square. We divide those and we get our F statistic. And then we would go look at an F table, but we're not gonna. We're just gonna use the significance, the p-value, and we can see that the omnibus test, the overall test, is significant. There is a difference. But we can assume it's between these two and the low level, so the medium and the high and the low, but we haven't tested it. So let's come down here and let's look at our multiple comparisons. And I can see that between the low and the medium, it's significantly different, and between the low and the high, it's significantly different. But that leaves us one level left to check, and that's between the medium and the high, and those are not significant. Now I failed to, let me just run this one more time and do options. I forgot to click mean plots. Let me just do it one more time and scroll down. And you can see that these guys are the same, but this guy is different than that one, and this guy is different than that one. Okay, I'm going to pause it there and pull up the other data set. Okay, so now I have the other data set up. This is chapter 12, page 547, the example on that page. Before we do anything else, I want to show you that this is a 2x3 factorial Anova. So I'm going to go to the crosstabs. I didn't do this in the PowerPoint, but I'm just going to show you. So here, I just want to look at the factors, right? So I'm going to do my rows, my rows as gender, and my columns as age group. And I will show you, we're not accounting for the pulse rates right now. We're just looking at the number of people in each of these groups. And I'm just going to say, okay. All right, so we see that we have 10 women in 18 to 29, 10 in 30 to 49, and 10 in 50 to 80, and then same for the males. So it's just giving you this. It's telling me how many are in here. When I do my descriptives, it'll give us the means for those groups, but I just wanted to show you that's how we have the data set up, and that it's a 2 by 1, 2, 3 factorial ANOVA. All right, so we're going to do analyze, and now we're out of the compare means. We're going down to this thing called general linear model, right? We're going to univariate, and that brings up this dialog box. We want our dependent variable to still be the pulse rate. We want age group to be a fixed factor and gender to be a fixed factor. And when I mean fixed, it's because we're saying what our categories are. Fixed and random factors are, it's a little bit of a complicated description, but when we don't know all the possible variations of something, it's random. But when we know the all possible, like we've specified all possible variations of it, we call it fixed. All right, so we're going to go to plots. And like I say in the PowerPoint, we have to think for a second. Where's our horizontal axis, and what do we want the separate lines to be? I would like separate lines for gender and then have the age group along the horizontal axis. So I bring gender over, I bring age group over, I click this add, and it gives me this interaction, right? And then I say, okay. I'm going to go to post hoc, and I want to see, is there differences? If you bring both of these guys over, it's going to tell you something. It's going to kick it out in the output because we don't need multiple comparisons for a dichotomous group. We only need it for the one with 3 or more. So we're going to say age group, and we're going to do LSD, not the drug, the least significant difference. We're going to go to options, and I want you to click descriptives. And now finally, SPSS will give us estimates of effect size, and we'll do homogeneity tests. We're going to say continue, and we're going to say okay. And we get a whole bunch of stuff. Okay, so here's just our case processing, our between subject factors. And this is the same thing I just did for you in the categorical or the crosstabs, right? It's just telling you how many are in each group. Now we can look, we see that 80 to 64, 80 to 76, 80 to 67. In each of these groups, the women are doing, have higher pulse rates than the men. All right, so let's go over here and let's look. We have violated the assumption of normality. They violated the assumption of homogeneity of variance. But we could do it based on this trim mean. We're just going to keep going. You just note it. Now here's the tests of between subject effects. This is your Anova table, but when you're doing factorial Anova, you have more things going on, right? So one thing that it's called partial eta squared is our estimate of effect size. And I always get tripped up when I ask for it because I look at this as though it's the significance, and I have to remind myself, no, that last column is not the sig level, this is the sig level. So just be careful when you're doing it not to just go here and say, oh, look, it's significant when it's not, right? So be careful when you're doing that. All right, so this corrected model is just output that the computer does, right? The intercept is, we're just going to ignore that for now. Later it calls it a constant. We're just going to ignore that for now. We're looking, here's our main effective age group, our main effective gender, and the interaction of age group and gender. Now what we have to do is we have to evaluate the interaction term first. So we're going to slide across, right? And the interaction between age group and gender is not significant. So we can say, okay, so there's no difference in males and females based on gender. So now we evaluate the main effect of age group. Is there a difference based on age group? And we see that no, there's not. It is not significantly different based on age group. Now we see, is there a difference based on gender? And we come across and we say, why, yes, there is. There is a significant difference based on gender. And knowing what I know, because I looked at my descriptives, I know that men have lower pulse rates than women. And we can look, we don't even need to evaluate the multiple comparisons because that three-group factor wasn't significant. Now look here. Here's our estimated marginal means of pulse rate. I see that women have higher pulse rates, which is not surprising. We saw that in the descriptive statistics. I see that men have lower pulse rates, and I told you in the PowerPoint that if they were parallel, then you could visually assess and come to the conclusion that there wouldn't be an significant interaction term. Now looking at this, I would say, whoa, that's not parallel. But we have tested it, and we have statistically evaluated that there is no significant interaction term. So this, even though it looks deceptive, it's not a significant interaction. All right, and then you would write that up, and I've given you how to do that in the PowerPoint. All right.